your problem with the buoyancy. So I've taken the liberty of drawing what I think the board should look like as it sort of sits in the water. So my blue line here is supposed to indicate roughly where I think the water hits the board. And as they say, the board is sort of floating with the wide side up. So that's what I've drawn here. And again, so it shouldn't really be taken to be a scale figure. But nevertheless, it gives you an idea. And this is the way I would start such a problem, is to try to get a visualization of what it is we're talking about. And then even though I've already drawn this once, I would go ahead and then kind of draw it again now from the side, now that I have a better idea of what it is I'm looking at. And that way we can basically draw like a free body diagram. So I would look at this from the side and try to imagine roughly where the water is hitting. It doesn't have to be perfect in this case. That's roughly about 2/3 of the way up. And then I would think about what forces are actually acting on this board. So there is the force of gravity pointed down. And because this system is in equilibrium, that is, it's not accelerating upward, downward, or sideways or anything like that, then there must be an equal and opposite force acting on it to keep it in equilibrium. And these two forces are given by, let's see, this would be the force of gravity. And instead of writing sort of mass times the acceleration due to gravity, for these buoyancy problems, what you want to do is usually write in terms of the density of the board. So the density of the object that's being weighed down by gravity, its volume, and then the acceleration due to gravity. So that's this downward force. And then the idea of Archimedes' principle, what it says, right, is that the buoyant force is equal to the weight of the water displaced. So in other words, we're going to have the density of water right here, the volume that's displaced, so the volume of the board that's actually underwater, and then again, the acceleration due to gravity. And as I said, because this is an equilibrium, these two things are equal. So we'll come over here to the side and we'll just equate these two things. So we have rho Vg, and that equals rho water, V prime G. And you can see that the acceleration to gravity doesn't matter. So it's interesting, right? So if you have a pool of water on Mars, then this will actually be the same. Anyway, so let's solve for our density. That's the question that we're actually after. And so what we'll get is we'll get the the volume displaced divided by the original volume times the density of water. Okay. And now we just want to go ahead and put in our values here. So what do we have? For our volume that's displaced, we have the 96 inches. Gonna run out of room there. We have the 3.5 inches. And then the amount that's underwater on the smallest side there is actually just 1 inch. All right. And then we divide by the total volume. So that's 96 inches, 3.5 inches. And then the full sort of height of the board is 1.5 inches. Okay. And I think what you can see is that the first two parts just cancel out. And let me write the density of water. So I'm going to use an approximation, which is about 1,000 kilograms per cubic meter. So I think it might actually technically be more like 997, but often you'll see people use about 1,000 kilograms per meter cubed. So as I was saying, these parts cancel out. And so ultimately what you're left with is 1 over 1/5, I'm sorry, 1 over 1/5, 1 over 1.5, which is 1 over 3/2, which is 2/3. So in fact, this is 2/3 of 1,000. And that is about 670. We'll write it approximately 670 kilograms per cubic meter. Okay, so I hope this has helped. And yeah, very interesting problem. These buoyancy problems are usually best solved by writing the force of gravity and the buoyant force in terms of densities, volumes, and the acceleration due to gravity. Good luck.